For most of human history, distance meant isolation. If you lived in the middle of nowhere, on a remote island, deep in the mountains, or far out at sea, getting connected to the modern world could require something enormous. Thousands of miles of cables, cell towers, fiber optic networks, data centers, and an entire infrastructure built on the ground. But now, something strange is happening. The internet is moving into the sky. Not as a science fiction concept, not as a futuristic experiment, but as a real commercial network with millions of customers around the world. And at the center of it is Starlink. As of 2026, SpaceX's Starlink network has grown to more than 10 million customers, while its constellation has expanded to more than 10,000 satellites in low Earth orbit. That makes Starlink one of the largest communications networks humanity has ever built. But here's the question. If satellites can beam high-speed internet almost anywhere on Earth, why do we still need fiber? Could thousands of satellites eventually replace the cables beneath our cities, across our oceans, and under our feet? The answer is more complicated than you might expect, because Starlink isn't actually creating a completely new internet. It's changing how you reach the internet. Think about what happens when you open a YouTube video. Your phone first connects to your Wi-Fi router. The request then travels through your local network, into your internet service provider, through routers and data centers, across fiber optic infrastructure, and eventually reaches the server holding the video. The server sends the data back, and that journey can cross thousands of miles. But most of the time, you barely notice. Why? Because fiber optics are incredibly fast. Inside a fiber cable, information travels as pulses of light. The cable may be buried beneath a city, attached to infrastructure, or stretched across the ocean floor. In fact, the global internet depends heavily on submarine cables. These cables carry enormous amounts of data between continents. So when you watch a video from a server on another side of the planet, your data may travel through an invisible highway of glass fibers beneath the ocean. Now replace part of that journey with space. Your phone still connects to your router, but instead of sending the data directly into a terrestrial network, the router sends it to a Starlink terminal. That terminal uses an electronically steered phased array antenna to send a radio signal toward a satellite overhead. The satellite receives the data. It can then send the information toward another satellite, a ground station, or a combination of both before the data enters the conventional internet. And the reverse happens when the information comes back to you. So Starlink isn't really an internet floating independently in space. It's more like a new bridge between your home and the existing global internet.
And the location of that bridge changes everything. Because traditional satellite internet had one enormous problem: distance. For decades, satellite internet relied heavily on geostationary satellites. These satellites orbit roughly 35,786 kilometers above Earth's equator. That's incredibly high. The advantage is obvious. One satellite can cover an enormous area. And because the satellite moves around Earth at the same rate Earth rotates, it appears almost stationary from the ground. A dish can point at it and stay there. Simple. Reliable. But there is a brutal trade-off: latency. Imagine sending a signal from your house to a satellite almost 36,000 kilometers above you, then down to a ground station, then through the internet, and then all the way back. The signal has to travel an enormous distance before your request is even completed. The speed of light is extremely fast, but space is extremely big. Traditional geostationary satellite connections could therefore produce latency of hundreds of milliseconds. For simple web browsing, that's annoying. For a video call, it becomes noticeable. For competitive online gaming, it can be disastrous. Starlink attacked the problem from a completely different direction. Instead of putting its satellites tens of thousands of kilometers away, put them only hundreds of kilometers above Earth. Most Starlink satellites operate in low Earth orbit, around 550 kilometers up. That's roughly 65 times closer than a geostationary satellite. And suddenly, the physics changes. The shorter distance means much lower latency. Starlink connections can often operate around 25 to 60 milliseconds under good conditions, bringing satellite internet much closer to the responsiveness people expect from terrestrial broadband. But there is a catch. A satellite only 550 kilometers above Earth doesn't see nearly as much of the planet as a satellite 36,000 kilometers away. And because it is moving extremely fast, it doesn't stay above one location. So one satellite passes overhead, then another takes its place, then another, and another. The network has to constantly move the connection from satellite to satellite. That's why Starlink doesn't need one giant satellite. It needs thousands. And SpaceX has been building exactly that. By mid-2026, the constellation had grown to roughly 10,000 operational satellites, with the network continuing to expand. SpaceX's launch cadence has become a critical part of the strategy. Reusable Falcon 9 rockets allow the company to repeatedly deploy new satellites while recovering the rocket's first stage. And in 2026, SpaceX began testing another important piece of the puzzle: next-generation Starlink V3 satellites. These satellites are designed to dramatically increase network capacity and bandwidth. That matters because building the world's largest satellite network is only half the challenge.
You also have to make sure millions of people can actually use it at the same time. And that brings us to one of Starlink's most impressive technologies: the antenna. A traditional satellite dish physically points toward a satellite. Starlink's terminal works differently. Inside the flat panel are many small antenna elements. By precisely changing the phase of the signals between those elements, the system can electronically steer the radio beam. No giant motor constantly swinging the dish around. No mechanical tracking system trying to chase a satellite moving through the sky at roughly 27,000 kilometers per hour. The electronics do the tracking. And this is one of the reasons Starlink can make thousands of fast-moving satellites behave like a single continuous network. But Starlink's biggest transformation may not even be happening in people's homes. It's happening in their pockets. Imagine you're hiking through a remote mountain range. No cell tower, no Wi-Fi, no fiber. Normally, your smartphone becomes almost useless the moment you leave terrestrial coverage. But what if your phone could talk directly to a satellite? No dish, no special terminal, just your ordinary smartphone. That is the next battlefield: direct to cell. SpaceX has been developing Starlink satellites equipped with much larger antennas, capable of communicating directly with compatible mobile phones. The concept is simple. Instead of your phone connecting to a cell tower on Earth, it can connect to a cellular tower in space. The first generation is focused on basic connectivity, such as messaging and limited data. But the long-term ambition is much bigger: broadband, voice, data, emergency communications, and eventually much more capable mobile connectivity. As of 2026, hundreds of millions of people are already within the reach of Starlink's direct-to-cell ecosystem through partnerships with mobile operators in multiple countries. And SpaceX isn't stopping there. The company is increasingly positioning Starlink as part of a much broader mobile strategy. In 2026, SpaceX agreed to acquire 65 megahertz of wireless spectrum from EchoStar for approximately $19.6 billion. That move is significant because it suggests SpaceX doesn't simply want to sell satellite internet. It wants to become a serious player in the mobile communications industry itself. And suddenly, the competition gets much bigger. Because Starlink isn't operating in an empty market. Amazon is building Amazon Leo, formerly known as Project Kuiper. AST Space Mobile is developing another approach to satellite-to-phone connectivity. Traditional telecommunications companies are partnering with satellite operators. And governments around the world are beginning to treat satellite connectivity as part of national communications infrastructure. The competition is becoming a race to build a second layer of the global internet. One layer on Earth, one layer above it. But does that mean terrestrial networks are doomed? Not even close, because Starlink has several serious weaknesses. The first is capacity. A satellite has finite bandwidth. If only a few people are using a satellite, the experience can be excellent. But if thousands of users in the same area are streaming high-resolution video at the same time, everyone has to share the available capacity. That means performance can decline during periods of heavy demand. The second problem is weather. Starlink uses radio frequencies that can be affected by heavy rain. Water can absorb and scatter electromagnetic energy, reducing signal strength. Under severe conditions, performance can degrade significantly. The third problem is obstruction.
The terminal needs a relatively clear view of the sky. Trees, buildings, mountains, roofs, anything blocking the path between the terminal and the satellites can interfere with the connection. And then there is cost. In many markets, Starlink is still more expensive than conventional broadband. In the United States, for example, current residential plans can start around the mid $50 range per month, depending on location and promotional pricing. That may be reasonable if your alternative is no internet at all, but if you already have inexpensive fiber delivering hundreds of megabits or even gigabit class speeds, fiber is extremely difficult to beat. And that's the most important point. Starlink doesn't necessarily need to beat fiber. It needs to reach places fiber cannot. Imagine two homes. The first is in the center of a major city. Fiber runs directly to the building. The neighborhood has dense infrastructure, there are multiple internet providers, the connection is fast, cheap, stable, and available around the clock. For this person, Starlink may be interesting, but it isn't revolutionary. Now imagine the second home. It's hundreds of kilometers from the nearest major city. Maybe it's on an island. Maybe it's a remote farm. Maybe it's in the Arctic. Maybe it's a mining operation. Maybe it's a research station. Maybe it's a ship crossing an ocean. Running fiber there could cost an enormous amount of money. Building towers could be difficult. Maintaining physical infrastructure could be even harder. But the sky is already there. Put a Starlink terminal on the roof, point it upward, and suddenly the location becomes part of the global network. That's where the economics change. For someone who already has excellent terrestrial broadband, Starlink is often a premium alternative. For someone with no reliable broadband at all, it can be a completely different proposition. And there was another use case that could become even more important: disaster recovery. When hurricanes, floods, wildfires, earthquakes, or war damage terrestrial infrastructure, fiber cables can be cut, cell towers can lose power, backhaul links can fail.
Entire communities can suddenly become disconnected. A satellite terminal powered by a generator or battery can provide an independent communications link. The infrastructure doesn't need to be repaired before the connection comes back. The network is already above you. This is why satellite connectivity is increasingly being treated not simply as a consumer product, but as a resilience technology. But there is a bigger question. What happens if Starlink succeeds far beyond its original purpose? What if satellites aren't just connecting remote homes? What if they become part of the normal cellular network? What if your phone automatically switches between terrestrial towers and satellites without you even knowing? What if airplanes, ships, cars, emergency responders, remote factories, and entire communities can move between networks seamlessly? At that point, the distinction between satellite internet and normal internet starts to disappear. And that may be the real revolution. Not replacing the internet on Earth, but removing the assumption that the internet has to stay on Earth. Still, there is a price for putting thousands upon thousands of satellites into orbit. Astronomers have raised concerns about the brightness of large satellite constellations and their interference with optical and radio observations. There are also growing questions about orbital congestion, collision risks, space debris, and the long-term environmental effects of repeatedly launching and deorbiting enormous numbers of spacecraft. As the constellation grows, these problems become harder to ignore. The future of satellite internet, therefore, isn't simply a technological race. It's also a race in regulation, spectrum, orbital management, sustainability, and economics. And Starlink now has competitors. Amazon Leo is building its own low Earth orbit constellation. AST Space Mobile is pursuing direct broadband connections to ordinary smartphones. Traditional telecom companies are forming partnerships. Governments are developing their own satellite strategies. The next decade could therefore look very different from the last one. We may not have one internet. We may have a layered network. Fiber for cities and data centers. 5G and other terrestrial networks for dense population centers. Satellites for oceans, remote regions, aviation, disaster zones, and global mobility. And direct-to-device satellites filling the gaps between them. So, is Starlink going to kill fiber optics? Probably not. At least not in the way people imagine.
Fiber is still extraordinarily difficult to beat when you need massive capacity, low latency, reliability, and low cost per gigabit. But Starlink is attacking a different problem: distance. The places where building a physical network is too expensive, too dangerous, too slow, or simply impossible. And that's why the most important thing about Starlink may not be the speed of its internet.
It may be the fact that, for the first time, the location of a person matters a little less. A village doesn't necessarily need a cable. A ship doesn't need a cell tower. A disaster zone doesn't need to wait for every line to be repaired. A smartphone may not always need a tower. The network can come from above. And once that becomes normal, the internet stops being something we build only across the planet. It becomes something that surrounds the planet. The age of fiber isn't ending. Something more interesting is happening. The internet is becoming three-dimensional.